Well, hello again. Long time no see. But after this, that's it. So, so in this lecture, we naturally continue talking about severe winds that are caused by thunderstorms. So, in principle, I said one could just start from this lecture, and that's all you need to know. Quite often to do proper research in wind engineering. But why not knowing what is creating those winds? Atmosphere is so beautiful. I mean, when you walk down the street and you see those severe clouds, you can at least imagine a little bit the dynamics of what is happening over there in those clouds. There is also a beautiful theory how hail forms in the clouds, how lightning forms, but unfortunately I don't have time to talk about all these things. So what I will talk about is downbursts. So I will talk about formation, a little bit about flow field, and then some measurements in modeling, but my focus here is not on measurements and modeling. And then similarly, I'll talk about tornadoes, formation, flow field, measurements, and modeling, but once again, the focus is not on measurements and modeling in this lecture. So first, downbursts. Here is a video of a downburst in I'm not sure where, maybe in Canada, but you can see how sudden they are. Nothing was happening. You see wind from right to left, very quickly advancing, and all of a sudden you have havoc. You have strong winds, visibility decreases, and even the cameraman cannot hold camera anymore properly. So that's a typical example of a downburst, very strong gust that suddenly appears, lasts for several minutes, and then disappears. Here is another example of a downburst. Nothing, you can see it with your own eyes, so to speak, how the gust comes in. There is lightning in the background, strong precipitation, destroyed trees, probably damaged cars, buildings, and all kinds of crazy weather. So, what is a downburst? You cannot. By the way, you know what this is? This is cold ice. That's how I drink whiskey every day. That's a frozen state of CO2, temperature negative 76. So this is a downburst on my desk. You see, cold air is hitting the surface, spreads, and look at this outflow that is spreading from this CO2, basically. You can see analogy. It took me 3 hours to edit this. Yeah, this is, gentleman asked, is it important to study motion of the cloud? You see, it's important how the cloud moves just like this. Yeah. Hits the surface and then spreads radially. Okay? So, in terms of formal, so to speak, definitions, if we go back to this picture, so here is a cloud, here is downdraft. This downdraft hits the surface of something and then spreads radially. That's downburst, okay? What is forming this downdraft? There is much more information in the notes that I provided, but generally these downdrafts are formed by evaporation and melting of we call hydrometeors. These are all particles in the cloud, water, ice, snow, whatever. Okay? And now, by definition, this outflow should be below 10 kilometers. Okay? And we can also subdivide downbursts into two classes known as microbursts, and that's when the outflow, damaging outflow, is below 4 kilometers, proposed by Fujita. and macrobursts when the outflow is above 4 kilometers. Okay? Now, we can also subdivide downbursts into dry and wet. Dry, let's first say wet. Wet are though this downdraft is associated with precipitation. But this precipitation can reach the surface or it can completely evaporate before reaching the surface. If the rain reaches the surface, these are wet downbursts. If the rain evaporates before surface, these are dry downbursts. So, formation. So here is a cloud. Now you should immediately say, but Professor Romanic, this cloud doesn't look like thunderstorm. And that's correct. That's because Microsoft PowerPoint doesn't understand atmospheric sciences. And they don't put a figure of thunderstorm. They only have this nice cloud. So I use nice cloud to represent thunderstorm. Here is height. Now we go a little bit into mathematics. Let's say this is density of a downdraft, density of the air of the downdraft in the storm. Here we have density of the surrounding air. D stands, rho is density, D is downdraft, air, A, is ambient atmosphere. Here we assume that pressures are the same, okay? This is not the case, but we will here assume it is. And then what are the forces? We have weight of the downdraft in this cloud. What would be, can anybody tell me, why the air doesn't go up? If you climb the mountain, the air density decreases. What is the force that acts in the vertical direction? If the air density decreases and pressure decreases with height, from previous lecture, what would be the force that is acting when there is pressure difference? Buoyancy. That's correct. Buoyancy is a combination of two forces. So that's correct, but not quite. What would be what constitutes buoyancy force? There are two forces that are making it. Equation of motion from previous lecture. What were the forces? Who can tell me force, any force in equation of motion? So there is gravity, I put it there, weight. There is pressure gradient force, there is Coriolis force, there are viscous forces, and that's pretty much it. Which force acts in the vertical direction if the pressure is decreasing with height? Pressure gradient force, okay? So there is pressure gradient force. Did you ever ask yourself, why is the air not accelerating in the vertical direction? Because it's engineering statics. Gravity pulls it down, pressure gradient force pulls it up, but they are in balance and the air is just calm. And they are so strongly in balance that you rarely have some vertical displacements. Wind blows predominantly horizontally. At any rate, so we go to the greatest law ever discovered, Newton's law, second Newton's law. Mass times acceleration is sum of all forces. Now, the big difference between fluid dynamics and atmospheric sciences in engineering. See, engineers, I'm also an engineer, but you study this bottle and you know the mass of this bottle and you say mass of this bottle is such and such. But in the atmosphere, how do you, 1 kilogram of air, where is it? This big, that big? It's very difficult to define mass in fluid. So we represent this law per mass, per unit mass, okay? So if you write just what are the forces in vertical direction, pressure gradient up, force up, weight down. Now you saw from previous lecture, pressure gradient force is this per unit mass, gravity per unit mass is this. So this is simply, you saw that equation previously. This is how air moves in the vertical direction, accelerates. If air doesn't accelerate, left side is 0, and that's everyday atmosphere you live in. Now, that downdraft over there is descending with respect to the ambient atmosphere, okay? So That is for the downdraft. For the ambient atmosphere, we have different equation of motion, okay? Which is this, and there is no acceleration. Now, I can rewrite this equation, and this is backbone of atmospheric sciences. This is known as hydrostatic equation. Pressure gradient force is in balance with gravity. Now, I take this and substitute over there, as you can see, and I get this equation over here. And my former PhD student said buoyancy, this is buoyancy. This right-hand side is buoyancy. So buoyancy is combination of the pressure gradient force and gravity. Or more formally said, buoyancy is the excess or deficit of the pressure gradient force in the vertical direction with respect to gravity. If these two forces are the same, there is no buoyancy. And then you can have positive or negative buoyancy. And that's the equation, okay? So quite often people call this term B. So vertical acceleration is buoyancy B, but that's what buoyancy is, okay? Is this clear? Now, the other thing, what is creating downdraft is, you see, if I go back here, is some liquid precipitation, liquid water, rain. But also you can have ice in the cloud. And these are, as I said, fancy called hydrometeors. And every particle of anything has weight. So each of these has its own weight associated with it. So we have mass times g, gravitational acceleration of liquid water, ice. And I put here, as you can see, that mass of hydrometeors is mass of all liquid water plus mass of all ice in the cloud. Now I can multiply this by g, and I get weight of these. Now, typically in atmospheric sciences, we divide this by m. So we get something known as mixing ratio. When you read literature, you will see mixing ratio in literature. That's just mass of anything divided by the mass of air. And this is force, mg. So you see, vertical acceleration is consequence of buoyancy, but it's also a consequence of how much precipitation you have in your downdraft. More precipitation, well, heavier downdraft. This is not buoyancy, this is known as precipitation loading of the downdraft, okay? And now I don't have time, there are other terms. What would be other term? Well, our assumption that pressure outside is equal pressure inside is not perfectly valid. So you could add, that's called, what, if you remember in previous lecture I said, vertical perturbation pressure gradient force. That would be that, and so on. But I cannot talk about everything. Now, in terms of contributions, this is from Knut 1989. It's a little bit busy, but this is cooling rate in joules per kilogram, and this is height. You can see sublimation of ice. Sublimation means direct transition from ice to water vapor, dominates in high regions of the cloud, and then melting starts dominating and evaporation starts dominating close to the surface, okay? Here is kind of in terms of lines. So if you would ask someone, or you, this is now what you should know, what is causing downdraft that results in strong winds? You might say, well, at high elevations, it's sublimation, then melting of ice, and then evaporation of liquid precipitation, okay? Any questions? So this is now very simple. These are just now pictures. So downdraft and outflow. We would separate it in stages. This would be horizontal cross-section, vertical cross-section. We have contact stage. This is also proposed by Theodore Fujita, who worked in this topic for decades in the 60s, 70s, 80s, and so on. So contact stage, outburst stage, and cushion stage. Now, contact is contact. Here, the strongest winds are usually below and a little bit behind this leading edge of the outflow. The strongest winds happen in the first 50 to 150 meters, okay? Average is about 80, 90 meters above ground. What is this cushion? Cold air. This is previous generation of cold air that descended towards the surface. And that air is cold, heavy, so it's difficult to displace. So the new air impinging down quite often sits a little bit on top of the old cold air. So the height of the maximum velocity sometimes tends to increase with time because of the accumulation of cold air from previous downdrafts. And yes, then from this view, you know, if you assume symmetry, there is no cloud motion, what one of you asked, then everything just spreads radially outwards. Now, if we go back, I look like some, this was not the best way to isolate my picture, but anyways. If we look into this downdraft again, and then outflow that is spreading, let's examine a little bit the dynamics of this front, this advancing front, gust front. So here is how it looks like. So the outflow that is advancing has several regions. You see now from previous lecture, you understand formation of new cloud at the leading edge of the outflow. And you have this strong outflow, you have backflow close to the surface associated with surface roughness. You have head of the outflow. The most forward region of the outflow is known as the nose or overhanging nose. There is a cushion of warm air underneath, and this is formed again because of friction. The jet is spreading across rough surface, so wind speed is weak close to the surface. So typically the profile of wind would be such that maximum winds are, as I said, are usually between 100 and 150, 200 meters above ground. Profoundly different from atmospheric boundary layer winds, where you have maximum wind at the top of the atmospheric boundary layer known as geostrophic wind or gradient wind. Geostrophic if isobars are straight, gradient if isobars are curved. Anyways, this is more 3D picture. This leading edge of the outflow, is rolling, and that is known ring vortex or sometimes also primary vortex. And you can see their axis of that. In this case, downdraft is also inclined. Inclination of the downdraft can be due to storm moving and or downdraft descending in the environment where you have atmospheric boundary layer winds, okay, that incline this downdraft. So to summarize, in terms of the profile you saw in previous lecture, atmospheric boundary layer is black, downburst is gray, profoundly different vertical profile of wind. Now I hope you understand why. Because of the dynamics of the downburst outflow that looks like a jet that is spreading. In terms of if you have an anemometer, time series are completely different. This is stationary wind. This is non-stationary wind. Downburst lasts about 10 minutes. Even below that, average is 7 minutes in North America, I think. So very short duration. And if you look into Gaussian properties, these winds are non-Gaussian. As you can see, K is kurtosis. Kurtosis of Gaussian process is 3. This is almost double. But you don't have to calculate it. You can see this distribution is not Gaussian. I mean. Okay, any questions? There is much more about formation of downbursts in the notes. And I go into thermodynamics a little bit, so you are exposed to that as well, but I don't have time to cover it here. Any questions? Okay. Now, in terms of measurements, this is a simple slide, of course. How do we investigate these phenomena? Well, the best is always field measurements. There is only one atmosphere, and the best is to go into the atmosphere and do measurements. But that's also the most expensive and most demanding in terms of organizing your field campaign and gathering people. So we can use anemometer, weather radars, LiDAR, satellites, and damage reports. Okay, I will talk about some of these, like LiDAR, a little bit more in a few slides. Okay, numerical models, numerical weather prediction models. These are models that give you weather forecast every day when you check on your smartphones. Computational fluid dynamics. There will be a lecture on that, and there is also cloud models that only simulate dynamics of the cloud. And then laboratory simulations, impinging jets, what one of you asked, but there are also gravity currents. Gravity currents are releasing mass of cold air into relatively warm environment, but these types of models are rarely, if ever, used in wind engineering. In wind engineering, impinging jet models dominate. Then there are also statistical simulations in terms of Monte Carlo modeling and other approaches. And yes, sorry, and there is analytical approach, which I love to, you have some equations and you try to find some simplified solution. So I said first is anemometers. Well, this is, I already showed what anemometers would measure. This is downburst measured on a 213 meters tall tower in the Netherlands. Measurement at 3 meters, 60 meters, 100, 180 meters. You can see steady state atmospheric boundary layer winds, transient downburst, steady state atmospheric boundary layer winds at different heights. Here is just to show you that this is not one event. You can see this, I analyzed it from across the world, Finland, Italy, Australia, and so on. United States, I mean, they are all similar. LiDAR, what is LiDAR? LiDAR is an instrument that looks like it's a box, like this box, that emits electromagnetic rays. And then electromagnetic radiation is backscattered of particles in the atmosphere. And some of that radiation comes back to the LiDAR. And thanks to the physics of Doppler shift, LiDAR can detect the motion of the air that backscattered this light. The same is the principle of radar. Radar is an instrument that sends electromagnetic rays. Just if I would splash water here, some of the water comes back and hits me. That's what the radar and LiDAR count on. That the rays will backscatter from particles in the atmosphere and some of that energy will come back and then it can be processed. The only difference between radar and a LiDAR is the wavelength. Radars have much longer wavelength than LiDARs. And there are, like everything in life, there are benefits of long wavelengths and there are negatives of long wavelengths. But here is a measurement by LiDAR. LiDAR was here in Italy, in Genoa. There is Morandi Bridge that collapsed a few years ago in 2018. And here I was involved in a study that measured thunderstorm outflow prior to the collapse of that bridge. The LiDAR these are just WindCube 400S, blah, 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 doesn't matter, some manufacturer. The LiDAR can scan 10 kilometers. Radars can scan hundreds of kilometers. Why? Because radars have much longer wavelength. And you know, if you study theory of light scattering, the shorter the wavelength, more scattering. That's why the sky is blue, by the way, and not red. Anyways, I could now go and talk about a million things, but it's just 10 kilometers. So here is the collapse of that bridge in Genoa in 2018. And you can see that, I don't know if this works. You can see that the wind collapsed during very strong wind, that the bridge collapsed during very strong wind conditions. You can see that winds are strong based on how trees behave. Now, this study that we did does not claim that bridge collapsed due to wind at all. But it is matter of fact that the winds were very strong during the collapse, okay? And we measured those winds using the LiDAR that I showed in the previous slide, okay? So what did we measure? So let me walk you through this. So let's start with the first one, okay? You can see this is the radial distance and the colors are wind speed. And wind speed between 9 hours, 15 minutes, 8 seconds in the morning. Yes, 9, yeah, to 9:50 to 15:57, yes. Phi is elevation of the scan in the atmosphere, 2.5 degrees, 5 degrees, 15, 10 degrees. So we scan at 2.5, then at 5, then at 7, then at 10. And here are now different instances in time. What do we see? We see that winds, LiDAR is in the center, and the region of strong winds is approaching LiDAR, as you can see, as the time is progressing. And winds are getting stronger and stronger. And eventually, we start having any data. Why don't we have data? What do you think? If you look into this picture, and I told you that LiDAR has very short wavelengths, why don't we have any data here, or here, or here? Say it again? Yes. Because short wavelengths are scattered very easily. The moment short wavelength electromagnetic radiation gets into precipitation, it is scattered very heavily and the signal is lost. So that's the drawback of having short wavelengths. When you have short wavelengths, you cannot scan anything in precipitation. But that's where the radar comes in. Radar has long wavelengths, and quite opposite, it can only scan when you have precipitation. So if this was radar, you would have no data here, but you would have data over there, okay? Here is where we had radar, but the radar wasn't Doppler radar, it was just measuring precipitation. So this is where the storm was at 9 in the morning. This is the precipitation region of the storm that I talked about, that we captured by this radar. And this is how the storm moved. So you can also now imagine dynamics from previous lecture, what is happening in the storm as it is moving. And this is where the storm was when the bridge collapsed at 9:36, okay? Went into the mountains and hovered there for some time. Another measurement of downburst was performed by Professor Burlando. Look at this beautiful outflow. This is like a textbook. This is a downburst that passed over LiDAR. You can literally see downdraft that spread radially the way we described in previous slides. Another way of doing this business is in wind tunnels, but I'm running out of time, so I will. Namely jets, what the gentleman said. You have strong jet impinging to the surface, it spreads, you put some probes, you measure velocity at different distances, and then you get some profiles of time series of velocities, okay? Here is how it looks like in the large wind tunnel in Canada. So here we visualize outflow with smoke, and you can see it spreads radially. You can see outflow. This is my voice. I always hate hearing my voice. Yeah, here is me doing the experiments. So here is me and two professors from Italy, and then a master student. And you can see the downburst is coming from right to left. So we weren't sure how strong it was, so we put master student first. If something happens, you can always get another master student, right? Okay, no, these are very weak, so no master students were harmed during these experiments, okay? Any questions? Yes. Yes, in wind engineering, you can quite often neglect air density, okay? That's why, you remember I said in wind engineering, we don't use gravity currents. Because atmosphere is so huge, the air in the atmosphere is descending from 2-3 kilometers. And if you want to replicate that dynamics in a wind tunnel that is 2 meters, you have to have huge air density differences, or you would have to have water splashing in the air. And that's not very good. So what we use is impinging jet that hits surface very hard. So entire kinematics is produced by fans mechanically. There is no density difference, it's isothermal. Okay, tornadoes. Tornadoes are the most, out of all wind systems on this planet, there is no wind system that is stronger than the tornado. The only winds that are stronger than tornadoes happen in jet streams, but jet streams are between troposphere and stratosphere, so nobody lives there. So here is a video of a tornado, and everybody is familiar, just tearing apart built environment, natural environment. This is in China a few weeks ago. Here is another video of a tornado, yet another. They just look magnificent, but they are also very, very dangerous. Tornadoes are classified because you cannot measure wind speed in a tornado. First, they're too high, they destroy anemometers, and second, it's very low probability that tornado will pass over your anemometer. So Professor Fujita suggested rating tornadoes by the potential to cause damage. And that's based on 3-second gusts, and here is Fujita scale, enhanced Fujita scale, EF0 weakest, EF5 strongest tornadoes. You don't have to, if this was exam, you wouldn't have to remember this. But what damage do you assess? Here are different damage indicators. So people look into houses, motels, automobile showrooms, different objects that tornadoes destroy. You go there, you inspect them, and you assess the strength of a tornado. How does a tornado form? There are over 100 people here. If you develop theory of tornado formation, Nobel Prize is waiting for you. Your name will be right next to Isaac Newton and greats. There is no complete theory of tornado formation. And there is no mathematical theory whatsoever of tornado formation. So what I will show here are some schematical descriptions, the best what people come up with, but none of them is complete. We don't have complete picture of tornado formation. One theory that I will show is, I am showing it for historical reasons, but people say it's not so accurate. First, you remember these vortex lines, vortex tubes from previous lecture. That's the key for tornado formation. So you have two vortex tubes, you have convection, hot air rising, that deforms these vortex tubes to be like that. And when you have convection, you have low pressure close to the surface, so the air converges towards the convection. You have cloud that doesn't look like thunderstorm, but it is thunderstorm. The whole system grows. You have bigger cloud. And now how do you get tornado? This was the question for decades. Because if you have this updraft, you see, this over here is rotating. This is rotating. But it's not rotating close to the surface. It's rotating up in the atmosphere. And updraft cannot bring this to the surface. So how do you bring rotation close to the surface of the Earth? And people postulated that you have to have downdraft. You have to have downdraft close to the updraft that will bring vortex lines close to the surface. And then eventually, they can even be cut off and you end up with tornado. When you have tornado, you have extremely strong vortex. So the convergence becomes even stronger than in the convection zone, and you have very strong vortex, okay? That was theory of tornado formation. But through numerical experiments, people figured out there is not that much evidence these days for this theory, but still, it's one of the theories of tornado formation. What's another theory? This theory says you don't have to have vorticity in the vertical direction. You start with horizontal vorticity, and thanks to downdraft, you get vorticity close to the surface. Another theory says if you started with vorticity in the vertical direction, if atmospheric boundary layer had vortex lines like so, these vortex lines start to converge, and vorticity is additive quantity, so you can add vorticity. So these vortex lines, you see two of them combine and vorticity increases. And then as the vorticity increases, convection increases, because as I said, there is a low pressure in the center of the vortex. So the air is rushing in. And eventually, when you gather enough vortex lines, you get very strong vortex. But this required that you start somehow with vorticity that existed prior to the storm, okay? This is the second theory of tornado formation. Third theory, one of the most complete theories. There is fourth, but I don't have time to explain it, okay? But there is probably even more. Third theory is the following. Downdraft. Downdraft has this ring vortex that we discussed. And this ring vortex is descending with the downdraft. So now again, you have to be a little bit imaginative. These are these ring vortices that are falling down with the downdraft. Close to the downdraft, you have updraft. So this updraft that is rotating, you saw in the previous lecture, this updraft is rotating and it deforms. Imagine you see this ring. Imagine downdraft lifting this part of the ring up. Again, it is tilting horizontal vorticity into vertical vorticity. And this vortex combines with that vortex and you get very strong tornado. And that explains, you remember I told you that tornadoes form where you have interaction between rear flank downdraft, RFD, rear flank downdraft and updraft. Is that clear? Tornado vortex. Here is a tornado in Nebraska from a few days ago. So if we look into this tornado, we can split it in several regions. 1, 2, 3, 4. I will go quickly through this. Region number 1 is where we have radial inflow into the tornado. Region number 4 is where we have radial inflow but heavily affected by surface roughness. So this is called boundary layer of tornado. This is called corner flow, where the flow comes in and goes up. And region number 2 is where we have a flow that is heavily rotating. We say that that flow is in cyclostrophic balance. Cyclostrophic balance is balance between the pressure gradient force in the radial direction and centrifugal force. And region number 5 is just top region in the parent cloud. This is the simplest ever model. So if you ask me, okay, if I stand in the center of tornado, how does wind speed changes with moving away from the center? It changes like this. This is tangential velocity. Velocity of rotation, it increases, then decreases. Pressure is dotted line, is changing. Pressure is the lowest in the center of the vortex. These are mathematical expressions for these, okay? People proposed all kinds of analytical models for tornadoes. In a book chapter from 2020, Professor Hangan and I summarized many of these various analytical models that people introduced. I have 1 more minute. Any questions? But this is pretty much on time, because now I'm going into simulations, which is not so important, I said. Simulations, in wind tunnels, simulations depend on something called swill ratio. Well, let me just skip, because I don't have time to go into depth, so I don't want to. How do we do research on tornadoes? The same as downbursts. Ideally, you do measurements, but look, I omitted anemometers. There is no anemometer measurements of tornadoes. They just get destroyed, okay? So we use all kinds of different. This is measurement by radar. You can see very strong wind speeds close to the surface. Maximum wind speed in this tornado. Look at this. Maximum wind speed in this Russell tornado that hit Russell in the United States. Maximum wind speed was below 5 meters. That's crazy. Compare that to atmospheric boundary layer wind, where the maximum wind is 1 kilometer above the ground. Here, maximum winds, and maybe they were even lower, but the radar cannot scan that close to the surface. Here is a tornado in that windy dome that I explained. Fans are sucking the air through the opening. Here we direct flow under the angle, so it swirls in. Here is a picture of a tornado-like vortex, because it's not tornado. I see you're taking picture, but you should take video of this. Yeah, this is much better if it works. here is a, I'm going to finish with this. Here is how we do experiments. Here is a community that was destroyed by a tornado close to Ottawa in Canada. We visualize things with smoke that is used in disco clubs. And here are pressure taps where we measure pressures, so we can later calculate responses. And now we start tornado. There are fans in the upper plenum. These suck the air in, and you get a tornado-like vortex, not real tornado. And you can see this opening called bell mouth can be translated. So we simulate how tornado passes over a community. And then you gather data, and then you have students and professors analyzing those data. Thank you very much. Any questions? If there are no questions, you're always welcome to find me somewhere here or send me email, and I'll be more than happy to answer, okay? Thank you.